Can everybody hear me? Okay. Okay, great. So I'll just get started now. Um, just to do this. Yeah. So just a quick overview of what we went over this week in lecture. So the main topics were were the kinetics of outer sphere electron transfer reactions, and a brief overview and I guess some examples of um, contemporary research into electrocatalysis. So I'll go over, I'll briefly go over Marcus theory, because I think that was the most important thing that we went over this week. And then I'll give some example, or for electrocatalysis, I'll, rather than go over uh, an example at length, I'll just kind of give an example system just to give you kind of a flavor of uh, why these systems are important and why you should care about them. Considering we didn't really go over, I guess, the basics of electrocatalysis yesterday. So, okay, so Marcus theory was essentially developed to describe the kinetics of outer sphere electron transfer mechanisms. So shown above here in this reaction is an example of what an outer sphere electron transfer would look like. So here we have cobaltocene, which is cobalt 2 plus, reacting with ferrocenium BF4, which is iron 3 plus. Cobaltocene is the reducing agent. Ferrocenium is the oxidizing agent. We're transferring a single electron from cobalt to iron, and we're getting cobaltocenium at the end and ferrocene and ferrocene. So the reason why you can think of this as an outer sphere mechanism is because the CP ligands that we're using here are quite large, and they include most of the coordination sphere of these first row transition metal ions. So we can't really use them as a suitable bridge to transfer an electron through. So Marcus theory, you need to remember, only predicts the rates of electron transfer under a couple of specific conditions. First and foremost, it really only works well for an outer sphere electron transfer mechanism. It's true that it can be adapted to suit inner sphere electron transfer mechanisms, but as it was formulated by Marcus, it doesn't work for inner sphere mechanisms. And second, the electron transfer needs to be adiabatic, or is assumed to be adiabatic in Marcus theory. But this is not always the case for reasons which I'll get into in a minute. So this is kind of the way that Marcus thought about inner or outer sphere electron transfers. Essentially, he thought that that the activation barrier people were observing came from the thermal activation of a donor-acceptor complex. So shown in this diagram is just that, where we have an electron donor represented by D and an acceptor represented by A. And we need to proceed up in energy on a vibrational energy spectrum in order to reach a threshold potential, delta G double dagger. And at that point, the electron transfer can occur. And then we cross over to this second potential well, which we have in which we have transferred an electron from the donor compound to the acceptor compound. And then this can then relax to its ground state. So the reason this activation barrier is composed of two main things. First is the reorganization of the inner sphere ligands, that is, those ligands that are directly bound to the metal compounds, or the donor and acceptor. and reorganization of the solvation shell around the compounds. So that is, if you have, let's say we're doing this reaction in water, the electric dipoles of each water molecule of surrounding these compounds will need to reorganize as soon as we'll need to reorganize as you proceed up this potential energy surface. And in doing so, you incur an energy penalty. So by simplifying the problem into these harmonic oscillator potential energy plots, you can use some simple geometry to back out this formula, which is the Marcus equation for delta G double dagger. On the right, we have a term that represents the Coulombic attraction or repulsion between the donor and acceptor compounds. But usually we want to neglect this because this has a term RDA, which is somewhat difficult to determine experimentally. So usually we'll do measurements of rate and things in solvents with high dielectric constants to drop this term to near zero, so that we can only focus on the important term over here. So the salient variables in this term are lambda and delta G naught. So delta G naught is our reaction driving force, which is just the separation between the bottom of the reactant parabola and the bottom of the product parabola. So this is essentially just the what makes your reaction spontaneous, right? So if this is negative, the reaction's spontaneous. If it's positive, the reaction's not spontaneous. You should know that from freshman/high school chemistry. So pretty simple. And lambda, which is the reorganization energy. So the best way to think about lambda is this is the energy penalty that you would be paying if you were to reorganize the inner sphere and outer sphere geometries of the reactants to those of the products without actually doing the electron transfer step. So it may be a bit easier to visualize that. So on one of these potential energy plots. So lambda is, where is it here? Okay, well, in any case, so lambda would ordinarily be equal to the distance from here, where delta G naught is equal to 0, up to the spot on the reactant parabola, if that makes sense. So if you were to draw a line from here up to where this parabola crosses that nuclear coordinate, that length would represent lambda. So here, delta G double dagger is equal to lambda over 4, and here delta G naught is equal to minus lambda. So one of the key things that came out of Marcus theory was the prediction of the inverted region, in which by overdriving the reaction, we can actually slow it down rather than speed it up. So that's illustrated here in these plots. So if we proceed, if we continue to lower our delta G naught value beyond minus lambda, we go from, instead of just staying at 0 delta G double dagger, which is what we would expect, we actually start increasing delta G double dagger again. And the reason for this is we need to actually change the geometry quite a bit in order to facilitate the electron transfer reaction by lowering making the reaction as exergonic as it is. So it's somewhat counterintuitive, but this is corroborated by experiment. So moving back to the second point that I mentioned earlier, in which Marcus theory only really applies to adiabatic processes. In the case where an electron transfer is non-adiabatic, we can just think of that as it's not 100% efficient. That is, as we go up this potential well, we may not actually proceed, we may not actually do the electron transfer when we get to the activation threshold. We may just relax back down to the reactants again. So what that looks like in terms of math is that our electron transfer rate is actually going to be smaller than what is represented by the Arrhenius law, plugging in the Marcus equation for delta G double dagger. So we add this term, this coefficient kappa to represent that, which is the adiabacity constant. If kappa is equal to 1 or approximately equal to 1, we can say that the reaction is adiabatic, and Marcus theory describes the electron transfer rates quite well. If kappa is less than 1, however, that means that the reaction rate is not well described by Marcus theory, and we have to use this variable parameter to rectify that. So the second point is kappa. We can use kappa to as a proxy for the donor-acceptor coupling energy, and this donor-acceptor coupling energy is going to depend on the amount of orbital overlap and the energy matching between the donor and acceptor compounds. So this kind of gets back into why compounds with extended pi system, or with ligands that have extended pi systems and good electron delocalization over the ligands, tend to engage in outer sphere electron transfer much more quickly than compounds that lack this. And that's because when the donor and acceptor compounds approach each other, because the electron wave function is delocalized over the ligands, it's much easier for it to actually transfer to the acceptor, from the donor to the acceptor, rather than in a case where it's really localized on the metal and you can't, it has no real overlap with the acceptor orbitals. So what does that look like in terms of these potential energy plots that we've been drawing? So for a process that's strongly adiabatic, the two parabola for the reactants and products will strongly mix, giving rise to this nice transition saddle point over which our reaction can occur. So this is going to be a case where we're strongly adiabatic, meaning the reactants and products are strongly mixing, essentially, in their potential energy surfaces. In the, I guess, the classical adiabatic case, it's just that, but less, where we have a higher activation barrier as a result. But when we get to the non-adiabatic case, we can see that the parabola don't mix very well at all. And as a result of this, only a small population of our reactants will go to products due to the fact that the electron transfer is not efficient at this transition, or at this threshold energy. And we can get to a point where we're strongly non-adiabatic enough that the electron transfer just will never occur, and we can excite it all we want, but it'll just continue to go back to the ground state, or relax back to the ground state rather than to an excited state. Yes. Somebody is raising their hand, I think. Sorry, I'm having a lot of trouble hearing you. If can you type your question in chat? Is there a chat? Yeah. Um, so I think it's less heat transfer and more energy transfer, right? You want to transfer this energy you've built up in the reactants into an electron transfer process that brings you to products, right? So this isn't like I don't think it's good to think of this as a heat transfer process, but more so of an energy transfer process. But keep in mind that these are vibrational energy spectra. Sorry, let me read that second part. Yeah. That is a good question. Yeah, agreed. That does seem like an odd term when you put it that way. I'm not really sure why then they call it an adiabatic coefficient. Yeah, sorry, I don't have a good answer for you on that actually, but that all I can say is that's what they call it. All right. Well, in any case, yeah. So going back to these plots, HAD, which is your HAD is going to correspond to the donor acceptor coupling energy, and that translates in these plots as 1/2 of the separation between the saddle point of your transition state energy and the corresponding excited state energy surface on these diagrams. If our HDA, I guess, is 0, that means we have no mixing and a non-adiabatic process. Yeah, I'll have to look up exactly what that term means in the context of electron transfer. Sorry about that. Okay, so with all of that said, we can move on to discussing electrocatalysis. So I think a point that was not really discussed in lecture, but I think is pretty important, is that electron transfer catalysts are pretty much ubiquitous in biochemistry, and all of them are extremely important. Because without them, life would not be possible. Furthermore, these complexes are all inform the design of synthetic mimics because they do very difficult electron and proton transfer processes that we would like to do on an industrial scale for whatever reason. So for instance, just to give an example of that, photosynthesis, we're converting carbon dioxide into essentially fuel that a biological system can use, and excreting oxygen and water. But so this is an industrially challenging process to do that we would, for obvious reasons, we would like to do, but we can't because it's not. It's quite energy intensive to get over the activation barrier required to do that. But biology does it at room temperature with just sunlight. So, so I guess the best way to think of what an electron transfer catalyst actually does is to look at a reaction coordinate diagram with respect to energy, or with energy on the y-axis. So we're going from reactants to products, but ordinarily we have a very high activation barrier here. But with the assistance of a catalyst, we can break this process down into many many small and easy steps that go through crucially low energy intermediates. And because we go through this pathway as opposed to this pathway, our net activation barrier is much lower. And as a result, we can do these processes under more mild conditions and more quickly, for that matter. So shown here on the right is what I'll be talking about in this review today, at least in general, not so much in depth. This is an example of the tail end, I guess I should say, of cellular respiration, in which we're taking glucose plus oxygen and converting it to water and CO2. So here is an example of the electron transfer pathway in which we're taking products of the citric acid cycle and oxidizing them and taking those resultant electrons, shuttling them through these different membrane proteins towards oxygen, which is the final energy sink. And through each of these electron transfer steps in complexes 1, 2, 3, 4, or in complexes 1, 2, 3, and 4, we couple these electron transfer steps to pumping protons across the inner mitochondrial membrane, and this builds up a concentration gradient which the body can, or which the ATP synthase can then leverage to generate ATP. So this is the main way in which ATP is generated in your body, and this is the main way we get energy out of this reaction. So it's pretty important. So to kind of get an idea of how transition metal chemistry is used in this process, we'll take a closer look at complex 4 as an example of this, in which we're taking electrons from cytochrome C and shuttling them into oxygen to form water. So this is the active site for complex 4, which is known as cytochrome C oxidase. Just to reiterate, the reaction we're doing here is 4 electrons plus 4 protons plus oxygen yields water. And ordinarily, this would be a very difficult reaction to do because we need to combine 5 things together at once plus 4 electrons all at once to form water. But through the use of this dinuclear active site, we can do this pretty easily and at ambient conditions, most importantly. So the way that just to, I guess, look at the structure of this active site, we can see that we have 2 parts. We have one iron heme complex down here, a copper tris-histidine complex up here, right above the iron heme, and an outer sphere tyrosine residue that hangs out near the active site, which is between these 2 metals. So we're starting out here with copper 1 and iron 2, and essentially this is how the catalytic cycle has been shown to proceed for oxygen reduction. So first, oxygen will associate with this bimetallic complex, in which it'll essentially just associate to iron and sit in between these 2 metals. Then the iron will transfer one of its electrons and the copper one of its electrons to form iron 3 and copper 2, and O2 2-, which is just peroxide, right? Then an electron will come from the protein from cytochrome C, or delivered from cytochrome C, to re-reduce the copper, at which point 2 protons will come in, react with the peroxide to form water, and a further electron will come from the iron porphyrin compound to form this iron oxo species shown here. We then get more electrons from cytochrome C and another proton. It's important to note that this outer sphere tyrosine moiety is working to stabilize all of these rather reactive intermediates and to make sure that only protons are transferred to this iron oxo species, which is really quite reactive. So as I said, another electron and another proton will be transferred here to form an iron 3 hydroxide. And this will then react with another proton to form the second equivalent of water. And then 2 more electrons will be shuttled in to regenerate our active site. Both of these electrons being from cytochrome C, coming in contact with the complex. So I think this is a really good system for illustrating how a good or how a competent catalyst works, in that we're taking this really challenging process and breaking it down into a lot of small elementary steps. You can kind of just ignore this side process just for simplicity's sake, but this is the primary process that cytochrome C oxidase will go through. But you can see that all of the electron transfer steps are separated. Most of the proton transfer steps involve either only 1 or 2 protons, which are much easier than transferring 4 at once. And all of these processes are decoupled from the oxygen association, which is crucial as well. So again, it's just a good example of a competent electrocatalyst, because we're going through a lot of low energy intermediates rather than trying to traverse this barrier all at once. Okay, if you want to read more in depth on cytochrome C oxidase and the catalytic cycle, I would suggest this reference down here. But as far as this specific system being covered on the exam, you don't have to worry about it. Just remember what makes a competent catalyst. It breaks down the reaction into tractable steps, essentially, without actually changing the reaction outcome. Okay, so just a couple of things before we end here. Remember, exam 2 is next week on Thursday, and you're going to be expected to know all of this, to recall all of this stuff, plus whatever we go over on Tuesday. Remember, it's important to note that everything that's been presented thus far is fair game, including stuff from exam 1, but we're going to definitely focus on stuff that you haven't seen on an exam before. So if you need to tailor your studies, focus on this stuff first, and then go back and review the stuff that you saw in exam 1. It's going to be administered on B courses, and it'll also be open book and open note. So that will be helpful for you, I think, but keep in mind the exam will be more difficult than last year's to help compensate for this. So just keep that in mind when you're preparing. We will, if we haven't already, we'll post last year's exam for you to look over and study. Okay, I think that's all I have. Yeah. Okay, so if anybody has any questions, please let me know. And because we have another, 25 minutes. So yeah, I'll be here for another 25 minutes to answer questions if you have them. No questions.